In this lesson, we're going to talk about comparison tests. Now, in the previous section, we talked about the integral test that allows us to determine whether or not a series converged or diverged by comparing it to an improper integral. And now we're going to look at how we can use the comparison test to determine whether a series converges or diverges by comparing it to another series that we know converges or diverges. And because we're getting more and more familiar with the geometric series and the P series, these are going to be the series that we use for comparison most of the time because we're so familiar with these. So the first theorem we're going to look at is called the comparison test. In this section, we're going to talk about the comparison test and the limit comparison test. So the comparison test is when we look for So the comparison test, we look for a series that we know converges. And if the series that we're trying to determine if it converges or diverges is less than that series, then we know that that series converges as well. Now, if we find a series that we know diverges, and we know the series that we're trying to determine if it converges or diverges is greater than that series, then that series must also diverge. So let's look at this example using the comparison test. In part A, we have the series 1 over n to the third plus 3n plus 2. Now, because this is an n to the third down here, I'm going to consider comparing it to 1 over n to the third. Usually we want to stick with geometric series and P series because those are the ones that we're familiar with. And with this P series, I know that this converges because my value of P is greater than 1. So I know that this converges. I also know that this series is going to be less than 1 over n to the third, what we're going to compare it to, because when I look at the values of this denominator, I'm adding values to n to the third in the denominator, which makes this get bigger faster, which makes the whole fraction get smaller faster. So I know that this is going to be less than this, which means the series is going to be less than that. And since we know that this converges, because it's a P series with P greater than 1, then using the comparison test, I know that the series that we're looking at here, this 1 over n to the third plus 3n plus 1, has to converge as well. Okay, looking at this next example, I am going to compare it to 1 over 2 to the n, because this is a geometric series and we're familiar with those when they converge and when they diverge. So this series here that we're trying to figure out, I know that this is going to be less than the series that we're comparing it to, because in the denominator, it grows faster than this denominator here, because we're taking 2 to the n plus 1, so we're adding 1 to the denominator, which makes the denominator get bigger faster, which means the whole fraction gets smaller faster. So I know this series is going to be less than this series. Now, because I know that this is a geometric sequence that converges, and I know that it converges because my common ratio, my r, is less than 1, I know that this converges, and therefore by the comparison theorem this must converge as well. Now, in this last example, using the comparison theorem, we have 1 over the natural log of n. I know that the natural log of n is going to be smaller than just n in the denominator, which means the fraction itself is going to get bigger because the denominator is smaller. So I know that the series 1 over the natural log of n is going to be greater than the series of 1 over n. And we know this is a p series. We also know specifically it's the harmonic series, when we talked about this before, that the harmonic series diverges. And when we look at it in terms of a p series, my p is 1. And when p is less than or equal to 1, this series diverges. So since I know that this series is bigger than the harmonic series, and I know the harmonic series diverges, then this series that we're looking for also diverges. Now, in the second theorem, we're going to look at what's called now the limit comparison test. So the previous theorem we talked about was the comparison test. Now we're going to look at the limit comparison test. So if we're trying to find whether or not a series converges, and we're looking at the series involving an, if we compare it to some bn and we divide and take the limit, if the limit is some value other than 0, then both those series, an or bn, both converge or diverge. So they do the same thing together. Now, if I take the limit as an over bn and I get equals to 0, then if I know that bn converges, then an converges. Now notice it doesn't say anything here about diverging. All I know is if the limit of this is 0 and I know that b of n converges, then I can say a of n converges. If I get the limit is 0 and I know b of n and I know bn diverges, then this is going to be inconclusive. Now the same thing goes for this last part here. If I divide an over bn and I take the limit as n goes to infinity, and I get infinity, okay, and this approaches infinity, if I know that bn diverges, then I know that an diverges as well. So this doesn't say anything about converging. That doesn't mean that they converge together as well. If bn converges and I get that the limit approaches infinity, then this test is inconclusive. Okay, let's look at the first example for this theorem. So I'm looking at the series 1 over the square root of n plus 1. Now I'm going to compare it to a p series of 1 over the square root of n. And if I rewrite it so that it looks more like the p series, it's going to be 1 over n to the 1/2. So this is a p series with p is equal to 1/2, and since I know p is less than 1, I know that this series is going to diverge. So when I take my sequence an and divide it by what we're comparing it to, which is our bn, and I take the limit as n goes to infinity, when I use some algebra manipulation and I clear the complex fraction, I'm going to get the limit as n goes to infinity of the square root of n over the square root of n plus 1. And then if I divide all the terms by the square root of n, I get the limit as n goes to infinity of 1 over 1 plus 1 over the square root of n. Now, as n approaches infinity, this gets smaller and smaller and approaches 0. So I'm left with 1 over 1. Now, if I take my an and I divide if I take my an and I divide by my bn and I take the limit as n goes to infinity and I get some limit other than 0, then by the first part of that theorem, we know that this series diverges, because if we get something other than 0, both series diverge or converge together. And since this diverges, then this is going to diverge as well. Looking at the second example of the limit comparison theorem, I have the series 2 to the n plus 1 over 3 to the n. I'm going to compare this to 2 to the n over 3 to the n, which I can rewrite as 2 over 3 to the n. And I'm comparing it to this because this is a geometric series, and I know when this geometric series converges or diverges. In this case, since my ratio is less than 1, I know that this series is going to converge. So we're comparing it. We don't have to compare it to a geometric or p-series. We don't have to compare it to geometric series or p-series. It's just more convenient because that's what we are familiar with. So I'm going to take 2 to the n plus 1 over 3 to the n, and I'm going to divide it by 2 to the n over 3 to the n, and I'm going to take the limit as n goes to infinity. So this is my an, and this is bn, what we're comparing it to. I'm going to take the limit as n approaches infinity. After I do some rearranging, after I use some algebra manipulation, I get that the limit as n goes to infinity is 3 to the n times 2 to the n plus 3 to the n over 2 to the n times 3 to the n. So I just took this fraction, found the reciprocal, and multiplied it by my an, and this is what I got here. Now, if I take and separate this into two fractions, so I'm going to take 3 to the n times 2 to the n over 2 to the n times 3 to the n plus 3 to the n over 2 to the n times 3 to the n. I'm going to split this into two fractions and simplify. When I take this over this, I get 1. When I take this over this, I get 1 over 2 to the n. So when I simplify this, I get the limit as n goes to infinity of 1 plus 1 over 2 to the n. Now, as n gets larger and larger, this approaches 0, which leaves me with 1. So, since by the first part of that limit comparison theorem, it says if you get some limit other than 0, then either both series diverge or both converge. Now, since we compared it to the geometric series of 2 over 3 to the n, and I know that that converges, I know that this series that we were looking at also converges, and that's by the first part in the limit comparison test. Okay, this last example is actually a little bit tricky. It took me a few times to figure out what to compare this to. So the first thing I looked at was I tried to compare it to the harmonic series. And so, because I know that this diverges. And so I took the limit of n over, so I took the limit of the natural log of n over n squared, all divided by 1 over n. And when I used my algebra, and I got it in the form where I could use L'Hopital, and I ended up getting that the limit of this, using the harmonic series, when I compare it, is 0. Now, because the theorem states, let's go back up and look. This one here says, when we compare it to this one, if you get a 0, that means if what you're comparing it to converges, then we know that the series that you're looking for converges. But I compared it to the harmonic series, which doesn't converge. So using the harmonic series gave me no answers. So I'm going to put down not conclusive. So I'm trying something else. I actually also tried, but I ran out of room. I also tried, because I saw this n squared, I tried 1 over n squared. And that didn't work or get me any answers either. So I tried 1 over n to the 3/2, because I noticed that when I flipped and multiplied, I wanted to make sure that I still had something in the denominator so that I could put it in the form of L'Hopital and get what I needed. So using n squared didn't help because that didn't leave me with anything in the denominator. So then I changed it to 1 over n to the 3/2, which left me, when I flipped and multiplied, with the square root of n in the denominator. So this one was a little bit tricky. It took a few times to figure out something that worked. But when I found that n over 3/2 worked, when I started manipulating this, I got it to the form where I have the natural log of n over the square root of n. And so it's in a form that I can use L'Hopital. So I took the derivative of the top and the bottom. So when I took the derivative of the top and the bottom, I got 1 over n. And then down here, I got 1/2 1 over square root of n. And when I cleaned it up, I got 2 over the square root of n, which gave me a limit of 0. Now, because I chose a p series that I know converged, because p is 3/2, which is greater than 1, then I can use option 2 to come up with a decision or a conclusion. So I could use option 2 to come up with the conclusion because I knew that Bn converged. And based on option number 2 here, it says, if you get the limit of 0 and you know that that series that if you know that that series that you're comparing it to converges, then the series that you're looking for also converges. And so by picking 1 over n to the 3/2, I know that this converges, so therefore the series natural log of n over n squared converges as well.